Good afternoon, dear listeners. We continue to study the theory of lines with distributed parameters. Today, I want to tell you about one invention that was made by me and my graduate student Alexander Semenyuk. This invention relates to the so-called problem of a long cable and relates to the theory of electric drive. At first glance, this doesn't apply to the theory of electrical engineering at all. But these inventions would not have been possible if Alexander and I didn't know the theory of lines with distributed parameters and didn't know the history of the transatlantic telegraph cable. Before the lecture, I ask you to subscribe to our channel so as not to miss the release of new lectures. Put likes. It will help spread knowledge among the maximum number of our listeners. Thank you. But first of all, traditionally, about our previous lecture. In our previous lecture, we learned that in order to create a non-distortion line, it's necessary that a special relationship be observed between the primary parameters of the line. The only possible way to fulfill this ratio is to artificially increase the primary inductance of the line. Theoretically, this patch was proposed by Oliver Heaviside, and practically it was implemented by Serbian scientist Mikhail Pupin. This implementation made possible the correct transmission of signals over the cable between Europe and America and ensured stable telegraph communications between the two continents for many years to come. But transatlantic cable and telegraphy are not the only possible application of a non-distortion line. You will talk about this in this lecture. Before we discuss the issue of a long cable, I'd like to tell you about asynchronous motors. Perhaps you already know the principle of their operations and their structure. However, what we need to understand for this lecture is that these motors are the most commonly used both in industry and in our homes. Every time we turn on a fan, a coffee grinder, or call an elevator, we activate an asynchronous motor. Very often, as in the case of elevator, for example, we need to control the rotation speed of such motor. Indeed, the elevator must smoothly start moving, reach its maximum speed, and then smoothly come to a stop. And that's where the difficulty arises. The fact is that the only effective way to control the motor speed is to change the frequency of the voltage that is applied to it. You can see the formula that relays the motor speed in rotation per minute and voltage frequency on this slide. This formula shows that the higher the frequency, the higher the speed of rotation of the motor. True, the speed also depends on the number of pairs of poles, P. But this parameter is directly related to the design of the motor and cannot be changed for each specific case. But after all, the frequency of the voltage in the network is also unchanged. From this, at first glance, it follows the speed of rotation of asynchronous motors cannot be changed. Let's look at the table on this slide. Nowadays, there are two industrial frequency standards in the world. In the United States of America, Canada, and Japan, and some other countries, the network's frequency is 60 Hz. But in Europe and many other countries, the frequency is 50 Hz. This table shows the rotation speed of motors with different number of pairs in different countries. For example, a motor with two pole pairs would rotate at 3,600 revolutions per minute in the United States and only 3,000 revolutions per minute in Europe. And it's impossible to change the rotation speed. This, in fact, is the main and very large problem. As we have already said, the most effective way to control the speed of rotation of an asynchronous motor is to change the frequency of the voltage. But if the frequency of the voltage in the network is unchanged, then this means that the motor must not be connected directly to the network, but to a device that allows you to change the frequency. This device is called a frequency converter. Look at this picture. It shows this way of connecting of motor. A frequency converter is connected directly to the electrical network, and an asynchronous motor is already connected to this converter. The principle of operation of the frequency converter is based on the so-called frequency pulse modulation. The output voltage of the converter is not sinusoidal. It is a sequence of rectangular pulses of different durations, as shown in this figure. But the electric current in the motor in this case will have a shape close to sinusoidal. Remember, when we studied the topic non-sinusoidal AC circuits, we said that an inductor approximates the shape of the current curve to a sinusoid if the voltage is not sinusoidal. But the coils of asynchronous motor are inductors. The waveform of the current in the motor is shown in red in this picture. Look, the longer the duration of the voltage pulse on the motor, the greater the value of its current. Therefore, if you change the duration of the voltage pulses according to a sinusoidal law, then the motor current will be sinusoidal, and by changing the frequency of voltage pulses, we can change the frequency of the motor current and hence the frequency of its rotation. In a nutshell, this is the principle of operation of a frequency-controlled electric drive. And here we come close to the problem of a long cable. It's clear that the motor and frequency converter are interconnected by a cable. But why this cable most often long? The fact is that a powerful frequency converter is a very expensive device. And most often in industry, we need to control the rotation speed of not one asynchronous motor, but several. These several motors can be located far from each other, for example, in different workshops of the plant or at a different beds of the seaport. If a separate frequency converter is used for each motor, then this is very unprofitable economically. Therefore, several electric motors are connected to one frequency converter using a very long electric cable. And here we return to the topic of our lectures. And such a cable is, as we already know, a line with distributed parameters. And lines with distributed parameters most often distort the waveform. Look at this picture. If we can ordinarily conventional cable and apply a rectangular voltage to its input, then at a distance of 10 meters from the input, the voltage shape will still be rectangular. But as the cable length increases, the voltage shape will be more and more different from the original. At a distance of 90 meters from the beginning of the line, we will not see a rectangular pulse at all. Thus, if you connect the frequency converter and motor with a conventional cable, then the motor located 10 meters from the converter will work normally, and at a distance of 90 meters it will not work correctly at all. This is the problem with a long cable. Many different methods have been proposed to solve it. For example, it was proposed to use high-pass filters, but none of these methods eliminates this problem. The problem of a long cable was studied by us at our department, the Department of Electromechanical Engineering of the University Odessa Polytechnic. When my graduate student Alexander and I understood what this problem was and how it was solved by many scientists, we were very surprised. After all, exactly, the same problem was solved 150 years ago. Only this problem was connected with the transmission of the telegraph signal and not with the frequency-controlled electric drive. After all, in fact, we need to ensure that rectangular voltage pulses are transmitted through the cable from the frequency converter to the motor without distortion. Only and everything. And the solution to this problem is well known to specialists in the field to telegraphy and telephony. You just need to make the cable non-distortion by using Pupin's coil for this. We suggested using a coaxial cable to transmit the signal from the frequency converter to the motor. And in order to for this cable to become no distortion, we proposed, follow Pupin, to include additional coils as shown here in the figure. These coils are included in the break of its outer conductive cable AME. This well-known method was new approach in the field of variable frequency drive. So it has been patented by us, and you can see the photocopy of the patent in this picture. See how the properties of the cable have changed after adding additional inductors. The first diagram on this slide shows the waveform of typically 9.5 meter cable. You have already seen this diagram on slide number 7. The second diagram shows that after turning on the additional inductors, the voltage shape at a distance of 95 meters is actually no different from a rectangular one. Moreover, as can be seen in the third diagram, this shape continues to remain rectangular even at a distance that is 3 times greater, up to 300 meters. Thus, the modernization of the cable by including additional inductors made it possible to increase the distance between the frequency converter and the electric motor by more than 3 times. Our lecture has come to an end. Today we learned that the most optimal way to control the speed of rotation of a synchronous motor is to use frequency converters. One of the main problems with the variable frequency drives is the problem of long cable, which is distortion of the voltage waveform and at the motor terminals in relation to the form at the terminals of the frequency converter. The traditional way to solve this problem is use sine filters. This lecture shows another way, based on the knowledge of processes in non-distortion transmission lines. We used additional inductors to make the communication line, transmission line between the frequency converter and the motor a non-distortion line. This method is more efficient and economical. In the following lectures, we will continue to study other very important and interesting features of lines with distributed parameters. Be sure to subscribe to our channel so you don't miss the next lecture. Thank you very much for your attention. I wish you success in studying the theory of electrical engineering.